Good evening, everyone. I will be starting the class soon. Just wait for a couple of minutes to see if anyone is joining, and then we will continue with today's class. Okay? So last class we had stopped with the assignment questions. Okay? Where we were dealing with the impedance, the diffusion effects were seen. So yeah, I'll just wait for a couple of minutes and then start today's class. Yes. We were looking into diffusion effects. So I hope my slides are visible. Yeah. So we were looking into diffusion effects, for the past 2 weeks. Yeah, that's what we are looking into. Before that, we were looking into impedance. We were considering a case where the reactions controlled by kinetics and rho. And we have the species getting easily available to the surface of the electrode so that the reaction happens. But in reality, sometimes the reaction rate is so high and the reactants will not be easily available. They cannot easily diffuse onto the surface. Similarly, the products cannot diffuse back. So all of this can result in a draw in the series, what to say, can affect the performance, or the mechanism is also hindered not just by the context in this case, but by the diffusion or the limitation of the products to diffuse out or the reactants to come onto the surface. So we say that the mass transfer limits are playing the role there. So as told over here, the reaction rate is fast, but action of species from onto the solution is low. So here there will be a thickness we say boundary line thickness across the electrode where we see that there's a concentration gradient and the bulk concentration is different from the surface concentration. So if we are doing some rotation, we see that the boundary layer thickness reduces. We can find this thickness out using Levitt's equation, where it's inversely proportional to the square root of the rotation. Then we saw about the what are the major, like we say we express flux and related to the reaction rate, which is again the proportion to current. So that's how we do the expressions. So when rotation is not there, When it's in, we see that charge transfer resistance is increasing when mass transfer operation comes to play. So then we saw the semi-infinite and the finite boundary layer condition. So there, how we are deriving this, we had looked into, right? So this how we then looked into unsteady state. So yeah, so we have to know how to derive the expressions and finally know what these equations are. You may expect probably you can get questions based on this in the final exam. So yeah, so this just took a long time to explain. So that's why I'm not going further into this now. We'll straight move into assignment. Okay. Then we have this is our second last class and we have a lot to wind up. So we'll be directly going into it. Yeah. So this assignment A, right? So we had discussed, your question up to question number 4 in this. So now we will be moving on to question number 5. Consider the following reaction. A giving B plus electron. Concentration of A and B in bulk solution are equal when a negative DC bias is applied, and was OCP under steady state conditions. Their options are, you have to say which one is correct. You have CA greater than B, CB. Option B is CA is less than CB. Option C is CA equal to CB. And option D, it could be any of the value depending on kinetic parameter value. Okay. Consider the following reaction. A giving B plus electron, and they say that the concentration of A and B in the bulk solution are equal. So A is the reactant, B is the product, and you have both concentration of A and B in the bulk to be equal. When you are applying a negative bias under steady state condition, which one of them is correct? So which one is correct? When negative when a negative bias is happening, you know that the backward reaction is happening. That is, the B will be continuously forming A, right? So obviously, when the reaction progresses, what is going to happen? And after that, when you stop on a steady state condition, you will have the product to be greater than the reactant. That means concentration of A is going to be greater than the concentration of B. Right? Is that the option given? So that's the answer. Now let's move on to the next question. In the above case, the relevant parameters are given as VA equal to 10 to the power minus 5 centimeters square per second, dB equal to 10 to the power minus 5 centimeters square per second, CA bulk equal to CB bulk equal to 100 millimolar, K10 equal to K minus 10 equal to 10 to the power minus 2 meter per second, B1 equal to 19 volt inverse, B2 equal to B minus 1 value equal to 19 volt inverse, boundary layer thickness equal to 10 micron, TTC equal to zero point 0.1 volt versus OCP, temperature equal to 25 degrees Celsius, then EIS equal to dash millimolar. So there's a question. So in this question, you are going to apply an electron principle. So there's a question. So question in the above case meaning A giving B plus electron. You have K1 and K minus 1. So the DC bias and all are given. You have to finally find out the concentration. So you understand that there is a mass transfer limitation happening in this question. So I mean it's related to mass transfer limitation. So now what is the first step when such a question comes? So the first question is to convert all the units to a standard unit so that you can proceed. So the first thing is dA equal to 10 to the power. So let's make it what you say practice. Then when you have to solve questions in impedance, when you get it for exam, convert everything into centimeter. It's preferable to have in centimeter because you will have in microns and all sometimes. So converting to meter instead of doing that, it's always better to convert it to because you'll have millimoles. So make a standard unit, be it meter or centimeter. I would prefer centimeter because your mostly your diffusivity will be in centimeters per second. Your what to say then you have the rate constant in meter per second. I would prefer to have it in centimeter because in diffusivity it is centimeter square. Converting to meter square can bring some confusion. So let's stick on to either centimeter or meter as per your choice. I'm going to stick on to centimeter. So dA and dB are given as 10 to the power minus 5 centimeters square per second. We have nothing to convert in this. Now, C bulk equal to CB bulk is equal to 100 millimolar. Yes, we have to convert. Equal to 10 to the 100 into 10 to the power minus 3 moles. Molar. Now, we have to convert into moles per second. So, mole are mole per liter. I want to convert it to mole per centimeter cube. So to do that, I'm going to multiply it with another 10 to the power minus 3. So totally 10 to the power minus 6 will come centimeter cube. Right? This is the conversion. So mole, you can multiply with 10 to the power minus 3 to get mole per centimeter cube. Into 10 to the power minus 3, you will get mole per centimeter cube. Now, what is the next thing? K1 0, K minus 1 is 10 to the power minus 2 meter per second. So meter to centimeter, you have to multiply by 100. So it becomes 1 centimeters per second. B1 and B minus 1, what is out of this? Value is going to be 19 minus 19. Be careful, I could have made a mistake there. B minus 1 is minus 19 volts. Now you have del, which is 10 micrometer. This boundary line thickness 10 to the 10 micron, which is 10 into 10 to the power minus 4 centimeter equal to 10 to the power minus 3 centimeter. Now EDC equal to zero point 0.1 volt versus OCP. So the first step is to convert all the units so that you don't make a mistake. Now K10 and K20, K1 DC, K1 K minus 1 DC is not given. K10, K minus 10 is given here. You also know what is B1. So we can find out K1 DC, which is K10 exponential B1 EDC. Then it is 1 centimeter per second, right? Into exponential 19 into zero point 0.1. So what is the value? Please find out the value. So I am getting a value of 6.686 centimeter per second. Please cross check. Okay. Now K minus 1 DC equal to K minus 1 0 exponential of B minus 1 EDC. So K minus 1 is 1 exponential minus 19 to zero point 0.1. Please again find out, substitute and find out. So you will get minus, 0.149 centimeter per second. Now you have to substitute in the equation. So equation we would have discussed it somewhere here. Like I'm not exactly able to find out where it is. In that case, you will have to do it by yourself. But we have discussed it in the last class. Let me just check if I can find that. Yeah, this equation. This equation is important, which is dACAB by del plus K minus 1 CB1 plus dA by dB K minus 1 DC CAB by dA by del plus K1 DC dA by dB K minus 1 DC. Let me write this down. So this is the equation you're going to use, which is CAS equal to dACAB by del plus K minus 1 DC CBB plus dA by dB K minus 1 DC CAB by dA by del plus K1 DC plus dA by dB K minus 1 50. So this is the equation. You may have to learn it by heart if you get questions. If you have been solving it for the exam might be difficult. So you may have to learn this by heart. Okay. Now let me substitute. You may have to do it for yourself instead of just copying it from here. Else, there are high chances you can make a mistake. K minus 1 is 0.149. C bulk is C bulk, Cb bulk equal 100 10 to the power minus 6, 10 to the minus 4 mole per centimeter cube. Okay. dA by dB power minus 5, 10 to the power minus 5, 0.149, 10 to the power minus 4. By dA 10 to the power minus 5, then equal to 10 to the power minus 3, plus K1 dC is 6.686, plus d by dB 10 to the power minus 5, 10 to the power minus 5, 0.149. Now, what are the values? Now, please solve it and let me know what is the value you're getting. So, finally, I'm getting the answer as 4.49 millimolar. This is the answer I'm getting. Right, now let's do the next question. So, you will have to solve the question. It's a little lengthy, it depends on how you're solving it easy. Okay, now this was question number 6. Now, relevant parameters are given as EA 10 to the power minus 5 centimeter square per second, dB equal to 10 to the power minus 5 centimeter square per second, Ca bulk equal to Cb bulk equal to 100 millimolar, K10 equal to K minus 10 equal to 10 to the power minus 2 meter per second, V1 equal to 19 volt inverse, V minus 1 equal to minus 90 volt inverse, boundary layer thickness equal to 10 micron, EDC equal to zero point 0.1 volt versus OCP, temperature is 25 degrees Celsius, then CBS equal to dash millimolar. So this is kind of continuation of the last question. We have already found out all these parameters, simplified it and changed it to single unit. So now the thing is, how is CBS related to function of CAS? So for that we have to again go to the last week's class. So we have already found out what CAS is. Now before that, if you remember, we had found out this expression, that is CBS equal to, let me write it down here, CBS equal to CBB plus dA by dB CAB minus CAS. So this is the expression you have to use. Again, you have to learn this also by heart. So that you might not spend, you will not need to spend time on deriving the expression during your examination. So what is CBB value? CAB equal to CBB equal to 10 to the power minus 4 molar. This, 10 to the power minus 5. Okay, I'll just write down directly, then it becomes easy. CBB equal to 10 to the power minus 4. DADB 10 to the power minus 5. What is CAB? 10 to the power minus 4. What is CAS? 4.499 10 to the power minus 6. So how much do you get when you solve this? You can use any method, calculator, however to solve this. So when I solve, I'm getting 1.9551 into 10 to the power minus 4 mole per centimeter cube. Okay. Now, if I'm converting it, the question is asked in millimolar, right? So I have to divide by 10 to the power minus 6 and I'll get 195.51 millimolar. Is this what you're getting? Or this is what you're supposed to get? That's the answer given here. Okay. So from last answer, type of questions you are expected to find out the surface concentration of the reactants and the products. So that is question number 6 and 7. Now let's move on to the next question. Okay, I hope there isn't any doubt on this. If you have, you can ask questions. Okay. And now question 8. In the above case, The steady state current value is dash nano ampere per centimeter square. Be careful with the unit. So it is a nano amps. So now how do you find out IF? The steady state. I can write as IF steady state as IF essence, right? So it is NF into rate of the reaction. So this we know. Now what is the rate of the reaction? It is A giving B. You have K1, K minus 1. This is the reaction, right? So forward minus backward. So that is K1 concentration of A minus K minus 1 concentration of B. Now it is at steady state. So in steady state, what happens is K1 is K1 dc, K minus 1 is K minus 1 dc, Ca is the surface concentration of the reactant CAS and surface concentration of the product is CBS. So now let us substitute. So CAS and CBS we got from the last two questions. Now let's substitute it. N value is 1 because it is a single electron transfer reaction. N equal to 1. So 96, 485 cent coulombs per mole. So coulombs per mole means it is going to be ampere second per mole. So all our units are in milliamps, etc. Right? So I can multiply it by 10 to the power 3. For the CA, substitute all the value. Have it in milliamp. So we are going to do this. Now substitute, find out the value. You have to do the calculation. So yeah, when I did this, I'm getting 91.59 milliamp per centimeter square as the answer. Okay, 91.59 milliamp per centimeter square. So which is coming in the range told, that is 90 and 95. So my answer should be correct. Now the next question, question number 9. In the above case, this charge transfer resistance is dash ohm centimeter square. Yeah, so you have to find out the charge transfer resistance. So what is the expression for charge transfer resistance? Have we written that explicitly here? Let me see. See here, we have written the expression ZF equal to YF inverse equal to 1 plus K1 DC by root of J omega dA plus K minus 1 DC root of J omega dB the whole divided by F plus B1 K1 DC C at X equal to 0 minus B minus 1 K minus 1 DC CB at X equal to 0. This is sum of RCT plus the wall work because of the reactant and the wall work due to the product. So the first term, which is 1 by F into B1 K1 DC CA at X equal to 0 CS minus, right, at the interface whatever at X equal to 0 means it is at the, we have already seen it's the interface, I mean the electrode interface, electrode surface, what is the concentration, that is CA at X equals 0, that is CAS, right? B minus 1 K minus 1 DC CB at X equal to 0, surface concentration of B. This is the RCT. So this part corresponds to RCT. This is, see then root omega and dA terms and dB, that's all corresponding to order. So this part is the RCT. So I'm going to use this expression RCT equal to 1 by F into B1 K1 DC CAS minus B minus 1 K minus 1 DC CBS. Now let me substitute the values. Ninety-six, 485. B1 is 90. 1 is 6.686 into 4.499 into 10 to the power minus 6 minus minus 19 into 0.149 into CBS is 1.9551 into 10 to the power minus 4. Now please do it and let me know what is the value you're getting. I'm just trying to solve it. Divided. Yeah. So I'm getting 9,125. Okay. Well, I'll be getting. So this is the value I'm getting. This is an ohm centimeter square. So this is a value I'm getting. Okay. Now let me move on to the next question. This question number 10. Question number 10. In the above case, the polarization resistance is mega ohm centimeter square. So what is the expression for polarization resistance? Okay. The expression, so as told, we have discussed this before, and then the expression is polarization resistance K1 DC del by F into K1 DC CAS B1 K1 DC CAS minus B minus 1 K1 DC CDS whole into DA. This is the total impedance expression. Now, how do we derive the expression? Okay, so we have ZF, the total Faraday resistance as the charge transfer resistance plus the Warburg impedance of A plus Warburg impedance of B. So which is 1 plus K1 DC tan H root J omega by dA del by root of J omega dA plus K minus 1 DC tan H root of J omega by dB into del whole divided by J omega dB, the whole in the root. So this entire thing when divided by x into V1 K1 dc CA at x equal to 0 with the CA is minus B minus 1 K minus 1 dc CB at x equal to 0. Now we have the polarization resistance. This is the polarization. So we're looking into how we derived or we reached there. Okay? So in polarization resistance, what is it when omega tends to 0? What is the total Faraday impedance? When omega tends to 0. So when omega tends to 0, what happens is tan h root of j omega dA into del divided by root of j omega dA. So I am applying limit omega tends to 0. This becomes this particular expression. I can tan h can be written by sine by cos h, right? I'm going to write as dA. So how we solve this is this entire expression becomes del sine h del j omega dA by dA del j omega by dA cos del j omega by dA. Okay, this is the expression we get. Now I can take out del by dA outside, and this becomes in the form of what? Limit omega tends to 0 tan x by x, where x becomes root of j omega by dA into del. So this is x. So this becomes del by dA. So when we are going to apply limit omega tends to 0 to zf, it becomes zt for polarization resistance, which is 1 plus k1 dc del by dA plus k minus 1 dc del by dB, the whole divided by f into b1 k1 dc ca at x equal to 0 minus b minus 1 k minus 1 dc cb at x equal to 0. Here ca at x equal to 0 equal to cas and cb at x equal to 0 equal to cbs. Same like before, we have found out all the value given. We said del value, all these are given in the questions. We substitute it, and finally, when I solved it, I got the value 6.28 ohmic centimeters. So this is the value. This was question 12? No, 10, right? No. This is the value which I got. Megaohm per centimeter square. This is the value I've got. You have to solve it and find out. Okay? Now the next question is question number 11. If EDC equal to 0 volt versus OCP, then charge transfer resistance is dash ohm centimeter square. Okay. So here You can use the expression as RT equal to RT by F square K10 CA bulk. Okay. And R value is 8.314 into 10 to the power 4 when you are accounting for centimeter and all. Okay. And once you solve it, I got a value of, let me see. Mm. So let me solve it. Okay. Yeah. So I'm getting the answer as 2713. Okay. So this is how we have to do this question. Now question 12. So you have to find out the polarization resistance. So which is same as this question we have done now. So the last question we did, question number 10. So please do it by yourself. So they say that the polarization resistance value should be between zero point 0.5 to zero point 0.6 mega ohm per centimeters. Mega ohm centimeters. But if you don't get the answer, let me know. Now the next question is, in the above case, at EDC equal to 0 volt versus OCP, but with semi-infinite boundary condition at a frequency of 100 Hz, calculate the Faraday impedance ZF, the real part of ZF, and your question 14. is the imaginary part. Because both questions are linked, I have written it together. So what I'm going to do is I'll be giving you the formula. You may have to try it yourself and let me know if you don't get the answer. So what is the formula when you have what is it, semi-infinite boundary condition? Take this one. So n is equal to 1 plus k1 dc tan hm del by root of j omega dA plus k minus 1 dc tan hm del by root of j omega dB the whole divided by f into d1 k1 dc c8 x equal to 0 minus k minus 1 dc b minus 1 cb at x equal to 0. This is the equation we are going to use. So zf equal to 1 plus k1 dc tan hm del root of j omega dA plus k minus 1 dc tan hm del by root of j omega dB the whole f b1 k1 dc cas minus k minus 1 dc b minus 1 cb1 sorry cbs cbs. So as per this question, your what to say, the real part should be between 50 to 52 kilo per centimeter square, and your imaginary part will be between minus 50 and minus 47. So this is the range in which your answer can vary. Okay, please do it by yourself. We know K1 DC, we know we know what is M, what is M is J omega by dA, right? So J omega by dA, no root. So solve this. You will get it in an imaginary. It will have both real and imaginary part. Find out. So you'll get the answer for 13th and 14th question. Okay. Now the last question in this is question 15. Under semi-infinite boundary conditions, for a simple electron transfer reaction, the concentration oscillations and potential oscillations. Just give me a moment. and potential oscillations have a phase offset of in radian. So the options are pi by 2, minus pi by 2, plus or minus pi by 2, minus pi by 2. So under semi-infinite boundary conditions for a simple electron transfer reaction, the concentration oscillation and potential oscillation have a phase offset of. So here, I don't exactly remember where we had discussed this, yes, but here, remember this portion where we dealt with pi by 4? Yes, this is what they're talking about. So it is plus or minus pi by 4. Yes, so with this, we have finished the discussion of assignment number for week 8. So I felt this week's assignment was really tough or more rigorous, I can say, when compared to the next set of portions. It wouldn't take much time for us to just discuss about brush through because there was around direct straight formulas to apply, and we'll be looking into that. Okay. So now we are going on to the next week, which is constant phase element, porous electrode. Okay. As the topic we are going to the small, I think like the next set of all the weeks are like the kind of short and crisp. So yeah, we're going to look into that because then after that we're going to deal with the different models and then non-linears. So let's just give a brief idea about what is constant phase element. So when we are plotting impedance or when we just get the data for impedance, we know at the lower x-axis you have the high frequency regime value, and when the time is increasing, we are getting the low frequency regime values. So ideally, it will be a semicircle or anything combination of semicircle. Let me draw it properly. So yeah, it's supposed to be a semicircle. Semicircle where you have a 90-degree with this. And it's a perfect semicircle kind. Perfect meaning here, whatever be the radius, it becomes the same for all the sides. So this is a perfect semicircle kind of impedance you can get. You can expect, not get, you can expect something which is a perfect semicircle. But in actual case, when you're doing the experiment, that okay, let me redraw this figure, same way. So there's the ideal case. Ideal of such a semicircle, we can model using a capacitor, right? We can model it using a capacitor. But in reality, what happens? So there's an ideal semicircle, we can expect to get something of this form. And you have the 90-degree curve. In reality, what you get can be something else. Something else meaning it looks like a semicircle, but it's not an exact semicircle. It's an exact semicircle, meaning it looks kind of depressed. Depressed meaning, why depressed? It is called as depressed semicircle because if we extend it, this is going to be a part of a mind my drawing. This is going to be a part of full circle. Although this is a depressed semicircle, when we are extending it, it becomes a part of a circle, and this angle is not 90 degree, it is less than 90 degree. So this is n pi by 2, some value of n. So n is less than 1. So this case where you are modeling it with an ideal so capacitor, you will get impedance as 1 by j omega c. So here, this depressed semicircle, which we are modeling, we can say it is constant phase element. And we can give ZCP, which is constant phase element as. Here you see 1 by j omega c. So instead of c, we'll use y0 and j omega will be raised to some power. Here's the formula you will use when you are using a constant phase element. So n value can be anything, can be 0, can be 1, it can be -1, sorry, n can be 0, n can be 1, n can be -1, n can be 0.5. So what is when n equal to 0? You'll get 1 by j omega raised to this is 1. You'll get 1 by y naught, which is kind of a resistance, a constant. Okay, so we are not looking into that case. So it's kind of resistive. Now when n equal to 1, it becomes 1 by j omega y naught, which is the capacitor. This is the case of a capacitor. Now what about 1 by, for n equal to -1, we'll get 1 by y0, j omega raised to -1, this means j omega. So here, because it is 1 -1, this 1 by y0 itself is a constant. So I can write y dash j omega where y dash is 1 by y0. So this is a what? Inductor, right? Now when n is 0.5, when 1 and -1, so value is 0.5, you can get, it will have what is a complex number. So this is the range in which you can vary the n value. So now the question, so I hope that's clear. Now the question is, why do you observe constant phase element behavior? Why do you observe a constant phase element behavior? So usually constant phase element behavior emerges from rough surface. Rough, rough electrode surface. So the surface may actually look smooth to our to our normal eyes, not under microscope, but just when visually it looks smooth. But it can have microscopic roughness. So this microscopic roughness can result in the CP behavior. So how does it result in CP behavior is because when there is a microscopic roughness, so individually there will be the surface will have different energy levels at every point, resulting in different CP behavior. So they result in different energy level at each point, and this results in CP behavior. Now we also have, because of this, the current distribution in each point will be different. So in order to calculate or understand the CP, there are two formulas. Let's look in this. The first one is called Mansfield, or however it is pronounced. Okay. And the next one is Bragg. So both these formulas are important. Okay. You may be asked to calculate the double layer capacitance, the effective double layer capacitance. So like you have CP behavior, so at each point you're saying the behavior, capacitive behavior is going to be different. So you have to find out the effective double layer capacitance behavior for that system. So for that you can use either of this formula. So in the question it can be given, calculate this using this formula, calculate using Bloch's formula. So you should know the formula by that. Y0 raised to 1 by n, RT raised to 1 minus n by n. Now Bloch's formula, the CDS effective for the Y0 raised to 1 by n, 1 by R solution plus 1 by charge transfer resistance to n minus 1 by n. So these are the two formula. Just give me a moment. So now we are going to look at the porous electrode. How will be the impedance response of a porous electrode? So for a porous electrode, the impedance response will be different from a planar electrode. Now let's see how it is. So in a porous electrode, if I say this is the electrode, you will have small channels. Okay, okay, and this entire thing, this is the electrode, and this is immersed in an electrolyte. This is porous. So you can see the channels. So how we'll consider this is you have the porous electrode, you have the channels, you will say this is the length of the porous electrode channels. So you have the electrode material, which is a conductor, and they have long cylindrical pores filled with electrolyte. Now we are considering this as a single pole, okay? And x equal to 0 and x equal to L. So here if I write x equal to 0, this will be at the electrode surface and x equal to L is the other end of the pole which is inside the electrode. So there is a model which is used to describe the porous model and this is called de-Levy model. Okay, so we have the pores, they are assumed to be cylindrical. So here we are considering only metal electrodes. So here when we are doing this, there are some conditions or some assumptions. We consider that potential is assumed same everywhere in the pore wall. Then axial diffusion. So we are only considering diffusion across the length and axial diffusion, which is with respect to the radius, is neglected. They are neglected. Now there's a condition, so I'm writing down here. If ideal capacitance behavior can be assumed in a small element within the pore, then we have a formula to consider the specific impedance of the pore wall electrolyte interface. Okay, I'll just write down. If ideal capacitance behavior can be assumed in small element of pore, then specific impedance of pore wall surface is given by, I can write the impedance, specific impedance at the interface as Z naught equal to ZF inverse plus J omega CDL all inverse. So they're in parallel. Okay. So here ZF is Faraday inverse. The other one is double layer impedance. So now we are assuming there is no reaction. That is Faraday impedance is infinite. So that means ZF inverse is 0. So now let's define some term. The first one is rho, which is specific. So that's different from del. Be careful with the notation. Length of the pore, radius of pore. Okay, I hope this is clear. We're considering a small channel, right? So it has a radius R and the length as L, and the specific resistivity of the electrolyte is delta rho. Now we are calculating potential drop across short distance delta x in the pole, which is given by delta E equal to minus I into R. This is known equation, right? So this is equation number 1. This is a known equation. V equal to IR. Same thing we have written for a small section delta x. So here R will be rho. L is small section x, so we don't have to consider the entire length of the channel, but of the pole, but a small section. It's already known it's a small section. By area. What is area here? This pi r square. We are considering cross section, so the area becomes pi r square. So this is equation number 3. So this is potential across a small distance delta x in the pole. Now, same way, potential drop per unit length across pore length, which is given by delta E by delta x dE by dx. I'm going to differentiate this. Which equation? D by dx of substitute 2, 3 and 2. What do you get? Minus I rho delta x by pi r square. So you will get minus rho I by pi r square. Dx by dx will be 1. So this is equation number 4. Okay. Now, current passing through cylindrical side wall. Now, if instead of considering the like this, we're going to consider across the wall of length del x, radius r, del I equal to minus E by Z dl 2 pi r delta x, which is equation number 5. Now we know limit delta when x tends to 0. I can write di by dx equal to minus E by Z dl, which we have to find out. Okay, 2 pi r. Z dl is minus E into j omega C dl. This is from equation number 1, 2 pi r. Now what we can do is this equation 6. Differentiate 4 with respect to x and substitute di by dx from 6. So what do you get? We get d square e by dx square equal to minus del by pi r square di by dx. Now I'm just going to e into j omega. I'm differentiating it di by dx from 4. If I differentiate it, this is what I'll get. Sorry, from 6. Yeah. This is equation 7. So d square e by dx square equal to e into 2 rho j omega c dl by r. This is equation 8. I hope you are able to follow. If you have any doubt, you can ask me. Okay. So now I can get something d square e by dx square is equal to e 2 rho by r j omega c dl. Now solution for this form is of the form E equal to C1 e to the power mx plus C2 e to the power minus mx, where m will be root of 2 rho by r j omega c dl. Now at boundary conditions we know at x equal to 0, v equal to EAC naught, and x equal to L, we know where it is ending. So the potential becomes 0. So we are going to substitute 11 and 12 in 9. So which is E equal to C1 e to the power mx plus C2 e to the power minus mx, where you will get EAC naught equal to C1 plus C2. Now if I'm going to substitute different, dE by dx, I have this equation, right? E equal to C1 e to the power mx plus C2 e to the power minus mx. Let's do d by dx. What do I get? C1m e to the power mx plus C2 minus m e to the power minus mx. Right? Now, if I d by dx equal to 0 at x equal to L. Boundary condition 2. If I substitute 0 equal to C1m e to the power ml minus C2m e to the power minus ml. Now, I know C2 from this equation. If I come and substitute over here, I'll get C1 e to the power ml plus EAC naught minus C1 e to the power minus ml equal to 0. Now, let me just rearrange C1 e to the power ml plus e to the power minus ml equal to EAC naught e to the power minus ml. C1 equal to EAC naught e to the power minus ml by e to the power ml plus e to the power minus ml. And C2 equal to EAC naught minus C1 equal to EAC naught e to the power ml by e to the power ml plus e to the power minus ml. So now, if I substitute both this in the equation, I'll get side 4 as E equal to EAC naught e to the power ml plus e to the power minus ml e to the power minus m l minus x plus e to the power. This is going to be the variation of potential inside the pore. Now, if I'm simplifying it or substitute, I mean, in terms of equation, becomes cos hm l minus x by cos hml. So this is the expression. Now, the next thing is potential gradient in any location inside the pore. dE by dx. I'm simply going to differentiate this expression. EAC naught sin hm L minus x minus m cos HML is a constant. Nothing will happen. I give this as equation 16. Now at surface, we know that the potential gradient is 0. Potential gradient is not 0. I'm going to find out what is the potential gradient at x equal to 0. Now if we have equation 4 and 17, which is 4. This is 4. Okay. This value is supposed to be equal to equation 17, right? That is dE by dx. This is from equation 4 that I get this. And this is supposed to be equal to this one. If I do this, I'll find out the current. So once we find out the impedance, the current, the next step is to find out the impedance of the pole. Which is Z4 equal to EAC naught by I. So this becomes del cot HML pi r square by m. Now what I'm going to do is I'm going to multiply or divide by L. So L, what do you get? Rho L by pi r square cot h ml by ml. So this ml can be written as a term like this. So if I do that, it becomes rho L by pi r square cot h. This is Z4. Now this one is given by another constant. So I can write this in this form. Okay. Now where rho resistance of the core is given by rho L by pi r square, or this is called resistance per unit length. This kappa is a dimensionless admittance. So you have five square it is ml square j omega CDL 2 into rho L square by R. Multiply by pi R, divide by pi R. You'll get y CDL 2 pi RL by pi R square rho L. This is kind of, I can say, ratio of admittance of double layer capacitor to admittance of solution. Correct. So now consider n such pores are there. So the total impedance will be R solution you have plus Z4 by N. So in complex plane plot, if you are looking, this total impedance, it will appear like a 45-degree line in high frequency limit and capacitive line in the low frequency limit. So this is how it's can be something like this. So this is its characteristic frequency. So if I write the characteristics, I can say in complex plane ZT appears as 45-degree line in high frequency limit and capacitive line in low frequency limit. Now there are some other terms you should know. Pore density, which is number of pore per unit area. So you know pore radius unit will be in micrometer. It's the pore radius and pore density of 10 to the power 6 pore per centimeter square. 1 centimeter, sorry, 1 micrometer, it is 10 to the minus centimeter. In that case, you can say that there are pore of 1 micro radius for every, so 10 micron per 10 micron square. So this is like, let me write it, then I'll explain. So pore density is called the number of pores you have per unit area. Now assume like the pore radius are going to be very small, like in microns. Now if I say there is a pore density of 10 to the power 6 pores per centimeter square. Okay, so 1 micron pore, that is something like 10 to the power minus 4 centimeter. So that means there is a pore of 1 micron radius for every 10 cross 10 square. We are saying so. So then there are how many? What is the pore size wall area? So it will be like 10 to the power 6 into 2 into 3.14 into 10 to the power minus 4 into 1 into 0.5. 31.4 centimeter square per centimeter square of geometric area. So the idea is when the number of pores are increasing, the magnitude of the impedance will be reducing, mainly at the low and mid frequency regime. So if I say let's say 45 and like this. So if this is for 2 into 10 to the power 6, now if I'm reducing it to 10 to the power 6 force, this will reduce to something like this. So the idea here is more number of force, impedance will reduce. Now same way, to see this is effect of number of pores. Now effect of pore radius, when radius is decreasing, impedance increases at mid and low frequency. So this will be like, so for the same case, okay. So if the impedance is like this, now when the pore, what to say, when the radius is reducing, so this becomes 1 micron and this is 0.5 micron. So these are few things you need to. So both our solution and the double layer plays a role. So that's why it starts from one solution and it moves away, and then you get a capacitive kind of behavior. Okay, so this is how we can derive the expression for porous and the non-porous for the porous electron, and how their impedance are related to the pore radius and the area. And number of pores actually. Okay. So for the next class, we'll look into the assignment problems based on this, and we'll be looking into the film form playing a role, and assignments based on that. And finally, the next class is going to be a last class, and we'll be winding up for that class. Okay. So if you have any doubts based on this, you can post comments and I can answer that. Yeah. Thank you all for joining. Thank you.